In this video we are going to look at how we can use the method of proof by induction to prove the binomial expansion of a plus b to the power n for positive integer values of n. So let's start by recalling what we already know about the binomial expansion. In the course of Unit 1 of the Mathematics A-Level course, you'll have encountered Pascal's triangle, which is the pattern that starts 1, 1, and the second row is 1, 2, 1, the third row is 1, 3, 3, 1, the fourth row is 1, 4, 6, 4, 1, fifth row is 1, 5, 10, 10, 5, 1. And you will have seen that it can be used as a quick means of expanding expressions of the form a plus b to the power n if n is a relatively small number. So for example, a plus b to the power 4 is exactly the same thing as 1 lot of a to the 4 plus 4 lots of a cubed b plus 6 lots of a squared b squared plus 4 lots of ab cubed plus b to the 4. It will have been pointed out in the course of Unit 1 that the numbers in Pascal's triangle are the same things as the numbers that we're going to write as NCR, where NCR is n factorial divided by n minus r factorial times by r factorial. So that the numbers in the nth row of Pascal's triangle are the numbers NCR for r equals 0, 1, 2, 3, all the way up to n. And that means that the expansion of a plus b to the power n can be written as nc0 times a to the n plus nc1 a to the n minus 1 times b plus nc2 times a to the n minus 2 b squared plus nc3 a to the n minus 3 b cubed, all the way along until we come to the final term, which is going to be ncn times b to the n. Now, all of this was established basically through a pattern spotting procedure, just using simple cases. And what we now need to do is we want to try and prove that this will work for all positive integer values of n. And ultimately, our proof is going to rely on a proof by induction. But before we can do the proof by induction, we need to establish a preliminary result. And that preliminary result says that the result of adding NCR minus 1 to NCR is simply n plus 1 CR. And we've got a little bit of algebra to establish this result. So let's start. So we've got NCR minus 1 plus NCR. Now we know the formula for NCR is n factorial over n minus r factorial, r factorial. So the second term on that side, and straight on our line, can be written as n factorial over n minus r factorial, r factorial. The first term is also going to be n factorial on the top, but on the bottom we're going to have n take away r minus 1 factorial times by r minus 1 factorial. Now we're hoping to show that that simplifies through to n plus 1 CR. And we know that n plus 1 CR is going to be the same thing as n plus 1 factorial divided by n plus 1 take away r factorial times by r factorial. So that's the target. So what we've got to try and do is we've got to try and move from the expression at the top of the page in red down to the expression on the bottom of the page, which is in purple. Well, the first thing to do with the expression at the top of the page is just to try and eliminate this double bracket we've got. We've got n, take away r minus 1, and that is exactly the same thing as n plus 1. Take away r. So the expression at the top of the first term on the right hand side at the top of the page can be just simplified slightly to become n factorial over n plus 1 minus r factorial times by r minus 1 factorial. And we haven't done anything at all to the second term. Let's pause for a moment or two, look at what we've got and look at what we're aiming for. What we're aiming for has got a common denominator, or has got a denominator of n plus 1 minus r factorial times by r factorial. So what we really want to do is try and get a denominator of n plus 1 minus r factorial times by r factorial for both of the two terms at the top of the page. Now this can be done reasonably simply. If we look at the first term, we've got a denominator of n plus 1 minus r factorial times by r minus 1 factorial. What I'd really rather like is not to have r minus 1 factorial, but to have r factorial. To have r factorial, I must multiply r minus 1 factorial by r. If I'm going to multiply the bottom of that first term by r, I must do the same to the top of that first term. Similarly, if I look at the second term on the right-hand side, to begin with, we've got n factorial over n minus r factorial, r factorial. I really want to have a denominator of n plus 1 minus r factorial times by r factorial. To turn the n minus r factorial into n plus 1 minus r factorial, I need to multiply the bottom of the second term by n plus 1 minus r. If I'm going to multiply the bottom by n plus 1 minus r, I must do the same to the top. Now, we've now got then that the first term on the right hand side is just n factorial times r over n plus 1 minus r factorial, and the second term on the right hand side is n factorial times by n plus 1 minus r over n plus 1 minus r factorial, Now, on the right hand side, we have a common factor between the two terms of n factorial over n plus 1 minus r factorial times by r factorial. And then we've got r from the first term on the right hand side and n plus 1 minus r from the second term on the right hand side. So what we've got in the green there is we've got r plus n plus 1 take away r, so that of course just simplifies down to n plus 1. So we've now got n factorial times by n plus 1 over n plus 1 minus r factorial, but n plus 1 times by n factorial is precisely n plus 1 factorial. So we've got exactly what we were aiming towards. Rather messy algebraic proof that. Okay, just see that you can follow the general gist of this proof. Before we move on to the proof proper of the binomial expansion, it's worth just commenting that what this little result is telling us is that the numbers NCR that we've been looking at behave or add up in exactly the same way as the adding rule of the numbers within Pascal's triangle. So we'll move on to the proof by induction of the binomial expansion. If we're going to do a proof by induction, and we want to prove that this result is true for all values, integer values of n greater than or equal to 1, we must start by proving the result is true for n equals 1. When n equals 1, the left-hand side is just a plus b to the power 1, which is a plus b. And the right-hand side, we've got 1c0 a to the 1 plus 1c1 b to the 1. Since 1c0 is equal to 1c1 and they're both equal to 1, that is equal to a plus b, so we certainly know the result is true for n equals 1. And then for the second step of the induction, we're going to assume that the expansion is correct when n equals k, and deduce that the result must also be true when n equals k plus 1. In other words, we've got to try and show that a plus b to the k plus 1 is equal to k plus 1 c0 a to the k plus 1 plus k plus 1 c1 a to the k times b plus k plus 1 c2 a to the k minus 1 times b squared plus k plus 1 c3 a to the k minus 2 b3 b cubed, all the way along until we come to k plus 1 c k plus 1 b to the k plus 1. So we know what we're starting with, which is a plus b to the k plus 1, and we've got our target expression. Well, a plus b to the k plus 1 is the same thing as a plus b times by a plus b to the k. Now we're assuming that we know the result is true for n equals k, so we know what the expansion of a plus b to the k is. So we can rewrite a plus b to the k plus 1 as a plus b times by the expansion of a plus b to the k. Now we've got to actually think about this expansion. Well, the very first term we're going to get is we're going to get a times by k c0 a to the k, which gives me k c0 times by a to the k plus 1. Now, if we look at the b multiplied by k c0 a to the k, that's going to give me k c0 times by a to the k b. But I'm also going to get an a to the k b term by multiplying the a by k c1 a to the k minus 1 b. So, put together, I'm going to get kc0 plus kc1 lots of a to the k times b. If I now have a think about terms that look like a to the k minus 1 times b squared, they're going to come from two places. First of all, I can have b times by kc1 a to the k minus 1 b together with a times by kc2 a to the k minus 2 b squared. Put the two together, I'm going to have kc1 plus kc2 lots of a to the k minus 1 b squared. And this pairing off process will carry on with the next term being kc2 plus kc3 times a to the k minus 2 b cubed. And this process of pairing up the terms will carry on until we reach kck minus 1 plus kck times ab to the power k. And then at the very end of the expansion we're going to have b times by kck b to the k. So that's going to give me kck times b to the k plus 1. Now it's at this stage that our little preliminary results need to be recalled. We know that kc0 is equal to 1 for every single value of k. That's simply saying that the first number in Pascal's triangle is 1 for each row. And similarly, that kck, the last number in each row of Pascal's triangle, is equal to 1. So kc0 is exactly the same as k plus 1 c0, and kck is exactly the same as k plus 1 k plus 1. And they're both equal to 1. And by the previous little result that we had, we know that kcr minus 1 add kcr is the same thing as k plus 1 cr. So in particular, we've got kc0 plus kc1 is going to be k plus 1 c1. kc1 plus kc2 is going to be k plus 1 c2. kc2 plus kc3 is going to be k plus 1 c3. And all the way along until we get to kck minus 1 plus kck is going to be the same thing as k plus 1 ck. So making use of that previous result, each of the brackets that we have got in the last blue line just becomes one of our combination terms that we actually want. So our target expression is now exactly the same as what we've got the line above. So what we've done now is we've proved that if the result is true for n equals k, then it is also true for n equals k plus 1. We know the result is true for n equals 1, so the result must be true for n equals 2. We know the result is true for n equals 2, so it must be true for n equals 3. We know the result is true for n equals 3, it must be true for n equals 4, etc. all the way along the positive integers. So we know that the result must be true for all positive integers n. I expect you'll agree with me that this is far from being a simple proof, and I think it's one that's very unlikely to be met under A-level examination conditions. It is one, though, that I think and would hope that you feel that you can follow the general steps of this proof of the binomial expansion.